So this is where we stopped. Let's move to the next slide. What are the issues to address in chemical looping that we still do not know, and therefore research is needed? And these are some of the research issues, immediate research issues that are needed, which are here. One is, of course, screening of selected oxygen carriers. Oh, then he has to get it. Right? 40% দেখাচ্ছে. Charging. So that's good. So these are the issues to address. Okay. It's not by no means these are the only issues to address. One is good to know that oxygen carriers can give some of their oxygens, but how much and at what rate? Effect of the volatile matter on oxygen carrier performance, because we say volatile matters are CO, hydrogen, and CH4 and CO2. That's fine, but also together with that some pollutants. That's also inevitable part of it. So in presence of those, how the oxygen carrier performs, we need to know, and that's what relates to the last one, effects of the polluting species, HCl, HCN, ammonia, sulfur dioxide, and hydrogen sulfide, because these are all poisons. These are known to be poisons or poisonous to catalysts, so they may be poisonous to the oxygen carriers. But if you can identify an oxygen carrier which is not affected by this very quickly, then obviously that will be good. So that's an important research area. These are the issues. Then you all raised the issues: attrition rate, the oxygen carrier itself. At what rate does it? Because ideally you would like to have a certain size so that it can circulate nicely. But if it gets finer and finer, it may be that it can give its oxygen carrier oxygen easily, maybe. But then the fine particles, as I also said before, that the fine particles have large specific surface area. Therefore, they can collect the minerals on their surface and become agglomerated. So it needs to be checked. Bed inventory and solid circulation rate requirement. At what rate you can extract the oxygen carriers from the fluidized bed, fluidized fuel reactor, and then through the passing it through the air reactor back into the fuel reactor, that's the solid circulation rate. That also needs to be calculated. In CFB, we know how that is to be calculated, but in CLC, that needs to be established. Effect of steam. Steam, as we have seen, it does it is required for in the carbon stripper. How it is calculated? There are certain formulas available which allows you to calculate this from the pressure drop measurements. So that will give you the flux. But in general, what happens is, one easy way of doing it is, this is how I used to do. Because you raised the question, so that gives me the opportunity. So so it goes in there, and then it goes to the cyclone. Okay. Or you can have an external heat exchanger here. So what you do is in the laboratory, you can do it in your day. Put a flapper valve here. Or here. Stop it for, shut it down for 1 minute or 2 minutes, calculate, see how much you are accumulating. I have done it easily. But in general, what is done then is you have pressure measurement here, the pressure measurement in the cyclone as well, here, biggest here. From this pressure measurements, you can calculate how the circulation flux is. So it is expressed as kg per time per area, per area. But it's very important. Solid circulation rate calculation or measurement in fluidized bed is extremely important. Without that, you don't know whether they are stuck somewhere, whether it's circulating or not. So the pressure drop measurements or the pressure indicators in a fluid bed tell you about the health of the fluidized bed, whether everything is going hunky-dory or not. It will give you engineering value. So there are two kinds of measurements that values that one can be interested. One is absolutely scientifically accurate value to the second place of decimal. Engineers in a large plant, 500 megawatt, 1000 megawatt plant, they are not interested in knowing that. They are interested in knowing it to the plus minus 5% level. So whether it is 95 kilograms per hour per meter square or 105 per hour per meter square, centered around 100, that's what they are interested. But as in a PhD thesis, perhaps you are interested as 97.68 or 102.59 or 102.5, something like that. So the point I'm making is that the formula and the pressure drop measurements are quite advanced enough to give you engineering approximations, and that's good enough. Okay. So I see in a lot of chapters, draft chapters, students bringing in numbers which are 102.5763, which doesn't make sense, because you cannot measure it. It's only done by the calculator's buttons. You can measure only to the, for your system, perhaps to the last place of the full digits. So it all is relative. So it can be as accurate as it should be. Then the inherent effect of the inherent catalytic compounds on carbon conversion. The coals which have catalytic elements present in them and have the temperature is good enough for the catalytic elements to be active. So you need to be mindful of that. CO2 and steam gasification kinetics of char particles under fluidized bed conditions. This is no different from non-CLC application. Okay. Effect of ash chemistry. This is the most important bit. Oxide mineral interaction. If the oxygen carriers start to interact with the minerals, then you got a problem. Ideally you not like to have that problem, have that interaction. Then you have the sintering and mineral deposition and the equilibrium and kinetic modeling. That's very, very important. That and we'll see an example of that later on. Okay. Then the oxygen carriers. What are the characteristics of oxygen carriers? Ideal characteristics, preferable characteristics of oxygen carriers. that they should have stable pore structure so that there is easy transfer of the oxygen to and from its matrix. With continuous passage through the reactor in hot environment, if the pore collapses, then that's not good. So physically they have to be stable. High mechanical, what it means, high mechanical and chemical stability. That means that they are not reacting, and mechanical stability, you know what it means. Yep. Low agglomeration propensity, so that they don't agglomerate between themselves. If one oxygen carrier agglomerates together with another oxygen carrier particle, then you have got a problem. Right? Low cost, which is a lifetime issue. Because if it is expensive, then you would like it to last longer. Low risk for health and safety, and that they have acceptable disposal characteristics. So if they have highly risky for handling purposes, then obviously you will not. So for example, you will not use a cesium oxide because it's radioactive. Huh? Yeah, so that's the mechanical stability. And then this bits, in addition, for coal-fired CLCs, minimum interaction between coal ash and oxygen carrier, which we have discussed, and the ability to separate easily from the ash particles. Those are two additional ones. So the top ones are valid predominantly for natural gas CLC or gas CLC. The bottom ones is for coal-fired CLC. So let's then talk about some of our work, and then through which we try to solve some of these issues. Okay, so that's why I have this slide again, that they have catalytic elements, and remember those two names, because we will be able to see them later on. So this is the first student who came to do CLC work with me from Jadavpur. He now works with a power company in US. He used this small setup that he developed. So he had a quartz reactor inside a furnace, and then there is a coal feeder, which drops the coal inside the reactor, and then there is thermocouple temperature measurement closer to the distributor plate. There is pressure drop measurement across it, and of course we have the gas being cooled and then analyzed. Okay. And we also have the facilities there for measuring steam or CO2 that we can put to the carbon to the char. We have nitrogen, we have oxygen supply as well if required to mimic it as an air reactor. So it's the same reactor, not two reactors, it's a tiny one, but you can get very fundamental information from these kinds of reactors. Tiny ones, nevertheless very well conceived. And then of course this is a standard thermogravimetric analyzer where you can do experiments over a long number of cycles and then see in a TGA, thermogravimetric analyzers, how their performance is holding up or degrading over different cycles. And of course then he went on to build a slightly larger one, again another quartz reactor as is shown here, that goes through another furnace. And sorry, this is the reactor. This is one reactor. This is another one. So as long as you have the furnace, you can make any types of. Yeah. And then we have this larger reactor, which is 4 meter tall. So you can see the students working there. So one is the fluidized bed, 150 millimeter diameter, 4 meter tall, and 6 inches and 8 inches of expanded freeboard, so that's 200 millimeters. And then it has its own gas analysis system here. The gas analyzers, we had the recirculation leg in there, but we cut it off for this application. We were running the fuel reactor as a bubbling bed, which is fine, but everything that we wanted to measure, we could measure. It had its own electrical heating, air going in, and of course all sorts of pressure loop measurements that are needed. Those are also there. Okay. And the coal was fed through this hopper continuously. So it's a continuous rig. So these are the ones that we designed and the students used to them. So first of all, you determine from the TGA through your screening test. When you recall in the issues slide, we identified these are the issues that you need to be worried about investigating. So he, being the first PhD student working on CLC, he had the luxury of testing a lot of oxygen carriers, some of which are the conventional ones, some of which are the manufactured ones, the synthetic ones. And then he, I will show it in the next slide. No. These are all their fuel reactor conditions, reduced conditions. It's in the reductor, and the fuel reactor is where the oxygen is scavenged from the oxygen carrier. So nothing to do with the reoxidation here. Reoxidation is investigated and reported in the next slide. So when you have a particular oxygen carrier, you know how much oxygen is there. And then from in the TGA, creating the fuel reactor's condition, then you find out how much weight it has lost. So you can then say that this much has been lost, and therefore this is the this is the non-oxidized, deoxidized. No. It is the reduced state weight divided by the oxidized state weight. $900. So here, this is only for the TGA. So here we are doing only the screening. That so many oxygen carriers are available. Which ones we will use? Which ones we will select? So the first thing you do is to see which one is able to give most of its oxygen. Those are the ones that are prime candidates. And then you will decide, okay, what's the cost of them? If an oxygen carrier can give up its 100% of its oxygen, but is extremely expensive, then no point. So this is just one side of the story. This is just seeing how much oxygen it can give up when it has been heated at a given rate to a certain temperature, and then see how much its weight has lost. So it's just from the standard TGA. Okay. So what we are seeing in here is that this synthetic one, not synthetic one, this composite one, the first one, it can give up about 47% of its oxygen. So no one is giving 100% of its oxygen, no one. So some give very little, say cobalt, etc. The third one, some give iron oxide. It reduces from iron oxide to metallic iron. That's why you have the name of the compound, asterisk, stroke the reduced form. The maximum reduced form is given there, but there may be a mix of the other lower valency form. Okay. So, so that's how it is. So this is the first set of screening studies that you do, and from there he then decided, okay, this one is a good candidate to look at more. This one could be another one, and this one could be another one. So this one is about 0.21, that one is about 0.3, and also he makes the note that this is also inexpensive in Australia, full of there. And this one is 0.2, but its reduction is quite heat releasing as well. So it gets sintered quite quickly, even at a very low temperature. So these are some of the things that you can see from the initial. So what is R naught? Yeah. So what is R naught? So Fe2O3, what is the percentage of oxygen in Fe2O3? Oxygen is 16, so that's 48. And iron is 56, so 112. So total 160, 48 out of 160 is 30%. So about 0.3 is its oxygen RO. That's the okay. But whether in real test conditions you will be able to get all of those, that remains to be seen. So then what he did was he looked at the 5-cycle tests first. Then he looked at okay, I'm eliminating this, I'm eliminating that. I want to look at a bit more on that. In 5 cycles, for the first one, which is so ABC are his publications here. So he is looking at that. The first one is nickel oxide, and one of the coals from that matrix, low ash, high volatile, one of those 3. The second one in B is with copper oxide. Third one is with iron oxide. Same coal, but with different oxygen carriers. He decided that from the previous slide, these are the 3 candidates that we will be focusing on. So then he noticed that for nickel oxide, in 5 cycles, the activity actually drops, and I will come to that. So what is happening, let's explain. This is where the reduction is taking place, and when it has reduced, that means it's not decreasing anymore, it's not losing any more of its weight, then it starts injecting coal. And in his case, the reducing agent was CO. So one of the, it's in the TGA. These are all in the TGA. So essentially, fuel reactor mimicking the fuel reactor, mimicking the air reactor. And then he goes up to that, and there he puts in more coal in here, because it's you have to do these experiments together with the coal. But unfortunately, when you have run this air cycle, oxidation cycle, the coal goes away, because here you have to do the reaction. Sorry, I said CO means it's actually not CO, it's actually with the volatiles coming from this coal with this this oxygen carrier. So the volatiles from this coal has reduced it to weight loss of the whole thing. So there, from there you then determine how much coal you loaded, how much coal has been, how much weight the coal can lose from pyrolysis tests in the TGA, which you do separately, and you separate that, take that, extract, subtract that out from these measurements, and then get this curve. So you don't get it directly from one set of TGA experiments. Or metal oxide, correct. And then here what remains is just the char and the reduced metal oxide. So what you do is then he then increased the he then put in air, and then that reoxidized it back while burning away all the char. And then he added more coal in, so that it could exactly the same amount of coal that was there in the first one, so that the second cycle starts exactly from the same condition, but it starts from here now. Because, so the metal oxide has actually lost some of its weight as well. So you are not touching the metal oxide at all. Or something else has happened to it. It may have been vaporized as well. We don't know yet. So anyway, so this is one cycle. So he did it in 5 cycles. Then when he plotted them, he sees that there is a very distinct drop in the reactivity. So that's how you first do it. You do it for this one. You see, this one is holding up. It's not decreasing as much rate as this. For the iron oxide, it's slightly better. So from this sort of 5 cycle test, you could do it for 10 cycles as well if you wanted. From this 5 cycle test, you quickly determine that this one is not good for further investigation. This maybe, we'll check it. This one definitely, we'll look it for investigation in a larger rig now. In the quartz reactor, this is in the TGA, so it's in a very tiny amount. So these are some of the observations that he made. He made the observation that the high coal combustion percentage by Fe2O3. So when you have the oxygen carrier and the coal, the oxygen carrier can not only give up its oxygen and so that the coal can burn, but some oxygen carriers can do it better than the other one. So in this instance, he figured out that the weight loss and the delivery of the oxygen from its matrix to the coal is much better in case of iron oxide. So from these tests, he went on to write his a very big chapter, and then he, together with the gas phase measurements that also he did, he just went into merrily onto his publications. So it's what you are predicting from here is that in 5 cycles, this is not losing its activity. It's very, very good. Yeah, both are same, but he also noticed that the copper oxide physically is agglomerating. And also this, he could not do it at 900, he had to do it at 800. So at 800, because the copper oxide was agglomerating, so at 800 what he noticed was that the coal combustion was a lot less. So that's how he decided that, okay, I will focus a bit more on this one, going to the next stage. Yeah, because that's, at the end of the day, that's your objective, so that you don't have too much to be converted into a carbon stripper, right? Remaining coal particles is drawn out, and then you simply burn it in the TGA. Then you find out how much was remained unburnt in the previous case, in the previous actual fuel reactor condition tests. TGA, you can do reduction reactions, you can do combustion. So gas inlet, there are gas inlets through which you can send any gas, nitrogen, helium, argon. Temperature you can control, you can set the temperature. Oxygen, hydrogen, and the flammable gases below the lower flammability limit. So you will, if it is hydrogen, then you will know that you won't be able to put in more than 5% hydrogen. The rest has to be inert gas, because 5% is the lower flammability limit of for hydrogen. So that's an example of what you can do. Okay, nothing else. Then, so he focused a bit more on iron oxide. He then went into doing 10 cycle. Then he went into doing 50 cycle tests in the TGA alone. But the important thing is to know what actually happens to the iron oxide. Is it going to the Fe3 to Fe2, I mean the valence state? Iron has different valence states, right? 3, 2, 0. Or even it can have anything between 3 and 2 as well, depending on how you are treating it, how long you are treating it. So then he subjected it to Xray diffraction, which all students do. So here are the symbols. This star symbol, spoken wheel symbol is for metallic iron. This is for iron 2. This is for iron 2.66. And this is for, this triangle sample is for iron 3. This is your starting point. Ideally, you would like to see a lot of those, but that's not what happens. But anyway, so in his fresh iron oxide, he has nothing but these ones detected by the Xray diffraction. So it's iron 3, all of them. So it's not a pre-reduced or anything. Then reduced iron oxide after a few cycles, I cannot recall what cycle is it. He sees lot of metallic iron, some woostite, Fe2, and a little bit of 2.66 as well, magnetite. And then when he again reoxidizes that all in the TGA, then he sees now it is all triangle. So it has come back here, it has come back to this state. Okay. So this is how the Xray diffraction can be used to check the valence status of it, but only after you have done the experiments, cooled them down, and then done the analysis in the lab. So these are all XC2. In this case, predominantly, but you also have a mix of Fe2 and you have a mix of Fe0, Fe2, and Fe2.66, which is Fe34. Then what we can also do is we have synchrotron next to Monash, and it's a highly competitive round of application. Some years we don't get in time. Some years we have to apply. Our application is to be judged by a panel of eminent scientists, and if we are lucky, if it is a good quality application, has scientific merit, technical merit, application merit, etc., then we can get. So when we get 2-3 days. So it's continuous, no stopping. So this is high temperature continuous synchrotron experiments, X-ray diffraction. What it does is, you take sample, you heat it up, and then you heat it up, and then at defined temperatures you take the diffractograms while it is hot. So you can literally see going from, and he did his experiments going all the way from 34 ambient temperature to all the way to 950, okay, and then he did some other experiments as well. So what he did was, and this we do it for our fuel cell research as well. So on the way up, you see how the structure or the valency is changing. At what temperature is it changing from Fe2O3 to FeO to Fe3O4 to Fe0? Because when it has reached the Fe0, if you can detect that temperature, then you know that that is the highest temperature that you would like to have in the fuel reactor, okay, for those particles. So this is a beautiful technique to identify that, because it's in situ. It is not ex situ. You are not cooling it down, because if you are cooling it down, the structures will change again and something will happen which you don't know what you are dealing with. So in as much as the previous ones were giving you some indication, but exactly when things were occurring you couldn't know, this is what you did know. So in the high temperature X-ray diffraction, what he did was, and the other students also do, is you take the diffractograms on the way up at different temperatures, and then you in a controlled manner you cool it, and exactly as those temperatures you take the diffractogram back again, so that you can then see if any structural changes are happening. You can do the experiments, reduction environment on the way up and oxidizing environment for some time, and then cooling it down under inert environment. So this is what he did. The bottom line is this, that the reduction of the iron oxide in this case, it started at 550 degrees centigrade. So it actually starts quite early, not at 900 where we operate. But obviously the longer you keep it, the higher temperature you take it to, the better it is for the release of the oxygen. But the oxygen release actually starts not at 900, it starts at 550. This is a vital information to have, because that's the time where the coal particles will have to be near the oxygen carrier as well. So that's a design issue. Then the other thing is that you can find from this test, when you are running it in oxidation mode, that after how many minutes of starting the oxidization, you get your oxidation state back. You get your original valency back. That's the other beauty of this test, which you could not figure out from any other tests so far. So here he found out from this, after 5 minutes, we get it back. That's it. So that's an indication, that's a design criteria for the air reactor, that you will have to give a reasonable amount of time. At least this is the starting information. Whether it gets all the valency back in 5 minutes or 6 minutes, that still remains to be seen, but at least what it is. So here, this also has implications for residence time in the two reactors. So that's the message that I want to give you, take from here. But these tests are done with tiny amount of samples. These tests are done with only about half a gram of samples, not even more than, not even that, about 300 milligram or so. So any particle size that you want to keep in the fluid bed. So this one, I think it was about 300 micron or so. So that he wanted to keep in his fluid bed. But without getting too hung up, the point I'm trying to make is, from TGA experiments, you can actually screen out this oxygen carrier is out, this is out, this is what investigating more. And then what you investigate, you do it in this sort of ways. By no means these are the only ways. No, this is when it starts. This is not when it finishes losing its valency. No, it's in the fuel reactor. It starts to lose its valency in the fuel reactor. I'm not talking about the air reactor yet. This is about the oxygen inside the fuel reactor. No. It has to go to the fuel reactor after it has gone to a temperature which is good enough for the carbon to be converted. Here we are looking at only how long and what temperature the oxygen transfer starts. Now oxygen is released in the fuel reactor. Where? So in the air reactor, you are supplying air to bring the valency back, to get the valency back. No. So what we are saying in here is that in the fuel reactor you have the fuel and the oxygen carrier, which is iron oxide. We want to know at what temperature inside the fuel reactor the iron oxide starts giving up its oxygen. Starts, not at what temperature it finishes. It starts giving up its temperature, oxygen starts at 550. Technically, you can say that, okay, I will run it at 550. The fuel reactor will run very long time at 550. But then the question you will ask yourself, is 550 a good temperature to convert the carbon? No. So you will have to take it to higher temperature. So that's why he did his experiments up to 950. Right? This experiments only tells you when it is beginning to give up its oxygen. Below 550 nothing is happening. Above 550 onwards, it's beginning to give up its oxygen. That's it. So you can actually see all of these peaks that, that you see in here. In real time, you can match it with its database and then can determine this peak means Fe2O3, this peak means Fe3O4, this peak means metallic iron. These are all crystalline phases. Remember, this is X-ray diffraction, and the location of the peaks is well defined in the literature. Now, not all peaks. So what happens is, each of these peaks that you see here, there are few other compounds that are present, okay? But only one or two of those belong to the one that you are looking at, and you are looking specifically for the existence of Fe2O3, Fe0, FeO, and Fe3O4. You are not looking at anything. So you will, when you start to see that Fe2O3 is beginning to appear, the peak corresponding to Fe2O3 is beginning to appear, the peak corresponding to Fe3O4 is, and Fe3O4 and FeO and Fe0 are beginning to appear, you know that it has started giving up its oxygen. So initially at ambient condition, there will be only Fe2O3 peak, no peaks for Fe0, no peaks for FeO, no peaks for Fe3O4. Then you take it to the next temperature, hold it for some time, take the diffractogram, and then you will see the peaks. Then immediately you will know whether it has moved away from Fe2O3 or not. If not, take to the next temperature, hold it there, look for peaks again. So what you can find is that at what temperature for the first time you see peaks corresponding to reduced form of iron, which are Fe3O4, FeO, and Fe0. So you can literally see it. So don't try to read anything from here apart from those two dotted lines. The message that I trying to give to you is that from this type of experiments, you can literally know, pinpoint what temperature the reduction starts, and at what temperature and after how long the oxidation completes. Okay. But these are done on only tiny amount of samples. As I said, about in the X-ray diffraction unit, you will be needing a very small crucible, so about 300 milligram of samples or thereabouts. But then your oxygen carrier can be in the bulk, and it's so if you want to do it over a bulk sample, then you have got another technique which is used by the physicists. It's called the Mossbauer spectroscopy. So Mossbauer spectroscopy, what it does is it measures the Fe3 and Fe2. It gives you, from the analysis of the spectra, Fe2, Fe3 ratio. Okay. So Mossbauer spectroscopy is done on a large amount of sample, so that you can actually see in the large amount of sample how much it has occurred, how much transformation has occurred, as opposed to in the X-ray diffraction, where you can see it only for a tiny amount of sample. But across the whole range of samples, whether that has taken place, the reduction has taken place or not, that can be determined better by the Mossbauer spectroscopy. So there, what you can do is exactly the same thing. You determine, and the codes are in here. This one is for hematite, this one is for Fe3O4 magnetite, this one is for FeO, which is oostite, and this one is for iron 0, alpha iron as we call it. So what we're saying is that this is where you can have the Fe2O3, but then after a certain time, after it, these are all done at 900, but after a certain time, you start to get the woostite, the metallic iron, and also a little bit of the magnetite. So this is done on a larger batch of samples, the mouse power spectroscopy, whereas the Xray diffraction is done on this much sample. So it is a complementary validation that what you are seeing on a small sample, most possibly if you do the mouse power spectroscopy on several number of samples, then you can determine, you can say with sufficient degree of confidence that yes, in the everything that is there in the fuel reactor has undergone a reduction rather than only some have gone through undergone reduction. Majority of them with sufficient degree of confidence, I can say that it has undergone reduction. So you need to do all of those. Otherwise, if you want to do XRD, which is very easy, then you have to do many of those, many samples, which is also possible. These days, you put it in the auto sampler, about 10 of them in one go. You can do that, and if you do 10 times, then you've got 100 samples done almost in a day or so. So you can determine it that way too. So that's how. So it's a difference between, as I mentioned when we are discussing fouling and slagging, doing EDX. EDX is doing at different points. Xray mapping is doing across the whole sample, the entire map. Yeah. The other technique that you can use is the temperature programmed reduction. So here what you can do is you have the oxygen carrier and you can send a reduction gas through it. In this case it is 5% hydrogen because, as I said, it's the anything over that you will be going into the over the flammability limit, lower flammability limit, so you will not be allowed to do that experiment in the lab. So you send that gas. You could also send CO in another experiment and CO plus H2 in another experiment, or for that matter, no one has tried it, with also methane in there. So you could literally see what happened. So interesting point is, this is hematite, it's TPR reduction. So up to that sort of temperature, nothing happens. Then at here it starts to happen, and there is a sharp peak at about 472.59 as measured by the thermocouple inside the TPR instrument. This is TPR is used extensively by the catalytic community, the catalyst research community. We used it for different purposes. Here you are seeing that it is starting to reduce in presence of hydrogen at 473. In the synchrotron, we saw that around 550. Between these two, you can get a feel for where exactly things happen. Okay. Even though we used the same amount of hydrogen in there, but this is research. Not every technique will give you exactly the same answer, but they will give you complementary answers from which you can do a holistic judgment. But that's not all. So this is at one of these temperatures, this transformation takes place. Another temperature slightly higher up, another transformation takes place. Another temperature, it takes place around 850 degree mark, another transformation takes place. So we then figured out, the student then figured out that this corresponds to the reduction from Fe2O3 to Fe3O4. This one is to FeO, and the next one is to metallic iron, Fe0. So this is a beautiful technique actually to cross-check I forgot to mention in here in the previous one that when you have Fe2O3, your objective is to go here. But whether you will be able to go there within the time and the temperature that you have is anybody's guess. Okay? Right. So ideally, you'd like to go from here to here. That means all the oxygen taken out. But that's not always happens. It's a function of time. It's a function of temperature. So if you don't give it sufficient time or temperature or both, then you will be, maybe you are stuck up to here. If you give a bit more, then maybe you're stuck up to here rather than going here. Or under an equilibrium condition, different proportions of all of these three, 2.66, 2, and 0. Not all 0, not all 2.6, not all 2, but definitely not 3 anymore. Let's keep that in mind, because when we discuss the Ellingham diagram later on, which is a kind of a phase diagram, we'll see it. So this is this is another complementary technique which is telling me that if I take it to that temperature and create a condition conducive to removing the maximum amount of oxygen, which means very, very good contact at that temperature between the volatile and the oxygen carrier, then I may be able to get all metallic iron. But if not, so what? We'll design the system accordingly, so that if we are asked to remain happy with only here, that's fine, which will mean lot of unconverted or partial converted iron oxide will remain. So it's just a matter of giving more of it in the system. Of course, it will have implications for heat transfer, etc., because more iron oxide means it will soak up more heat inside the fuel reactor, even though it will give up a lot of that heat, more than that in the air reactor. So nothing is really fully negative. Okay? Important thing is, between these techniques, the TGA, the room temperature X-ray diffraction, continuous and high temperature X-ray diffraction, TPR, you get a very solid, well-rounded, holistic picture, as we call it, for what needs to be done to the iron oxide, or for that matter the oxygen carrier, so that you get the best objective attained that you set out to achieve. Okay? And there is no shortcut for doing this. And the modeler, if the student is doing the modeling of the system, he needs to know all of these things. Otherwise, no matter how many times the others say or I say to the student, it will not necessarily gel. Really, you need to experience it. Analytical instruments are available. You learn it. You get suggestions from your supervisor and from your seniors who have worked in that area. Go for it, learn it, appreciate it, because this is the last time that you will be learning to do things on your own during the PhD. After that, you will be expected to supervise, and you will be expected to talk. You will be expected to tell your story. No shortcuts. So the more you apply yourself, the more you try to learn from asking questions, which you are doing rightly, the more you will learn. That's why I tell students that please ask questions, because that's how only you get your, through the discussions, your everything is, it becomes more clear to everyone. Okay, so that's on the analytical instrument side, and let's then come back to a little bit on the experimental work and your favorite model, shrinking core model. Nitesh loves this model. He was trying to convince me the other day that even in training for gasifier, he would love to apply it, shrinking core model. So I would love to know from you 1 year's time, what did you find when you have built your reactor, operated it, and then yeah. So people have used it, and when Nitesh Shah uses it, then I would love to hear from his. Yeah. So anyway, without digressing too much, even from the TGA type of experiments, TGA is nothing but a fixed bed, right? To some extent, everything is fixed. Even though in a fixed bed gasifier or fixed bed reactor, the whole fixed lump, it descends. Only difference, it doesn't descend, but you can argue that the lump of oxygen carrier and the coal, that shrinks, so in a way that descends. So there are similarities, there are dissimilarities, as long as you say it clearly, spell it out clearly in your paper or chapters, that's fine. So the shrinking core model is very well known. You take it from the literature, and then with different level of reduction gases. He didn't do with hydrogen at all. He took a lot of risk in going well over the lower flammability limit with CO. So we decided, okay, let's take the risk, and then if anything happens to the TGA, then I'll have to look at it money-wise. So without going into any of the details, the standard shrinking core model, which measure the experiments, it measures how much the weight, at what rate the weight is lost as a function of time. So it's dx dt over time, or dx dt over temperature, that however you plot it comes directly from the experiments. And then the shrinking core model also has those parameters, and some of those require requires you to give the inputs for your conditions. And this is what he roughly sees. It is too good to be true, but that's how it is. That over a period of, under that condition inside the TGA, over a period of about 12 minutes, shrinking core model for the fixed bed fuel reactor reasonably well predicts this, and he has actually published it in Chemical Engineering Journal or wherever. And then he does exactly the same thing, but this time for the air. So the idea here is to see whether any of the existing models can predict the behavior of particles of a certain size for different concentration of reducing gases, so that you can put that model directly into the CFD and use that CFD for scaling up purposes. Nothing else, nothing else. Now, I couldn't tell that instead of 28% CO in here, if he had a mix of 28% CO and 28% hydrogen, whether that will match, follow shrinking core model, don't know. Someone has to do it and find it out. Maybe not, maybe yes. But the good thing is that this is the way the TGA experiments can be utilized to validate, invalidate, or other way check whether an existing model works. If it doesn't work, then of course you can modify it. Okay, it's a curve fitting, nothing else. So this So this is all in the TGA. So from the TGA, then all the analytical work, etc. You have got, again, you have expanded your that holistic level of knowledge. Now you take it to the fluidized bed. Of course, you will take it to the smallest fluidized bed that you know you can handle, you can operate with a good degree of certainty. You don't jump all on a sudden to the one that you have you don't know much about. If your seniors have done it, then obviously there is a case for going straight into it, as we are doing the 100-hour test now. One other thing that we do is to do this sort of simple, complex looking calculations. This is called Ellingham diagram. Does anyone know what Ellingham diagram is? Yeah, but what it does. So Ellingham diagram, it is plotted to determine from experimental data what will be the stable species and at what temperature, provided the starting compound is subjected to a certain amount of reducing gas, or for that matter any gas. So this is just one example, nothing else. This is calculation, so no problem with using 75% CO and 25% hydrogen. You could use anything, right? But important thing is, what he did was he took 100 gram Fe2O3 in his calculation. These are available through softwares, standard softwares. Some of the readily available inexpensive softwares, as well as FactSage, which we showed the other day, that in relation to the prediction of the viscosity and the compounds, crystalline compounds, amorphous compounds, etc., how those can be predicted. Exactly the same software was used for it, but there are many other softwares, not just that. That one is the only one. It's not the case. So what it did was took 100 gram Fe2O3, took that reacting gas, and that, yeah, okay, let's go to that. And then this is the line which is Fe3O4, I think. Is that right? Let me go here. Yeah, let me go this, because from this angle I can't see it. So this is where the Fe3O4, okay, which is a solid phase. As you mix this gas with that much Fe2O3 and heat it up, then you will see that this is dropping, Fe2O3 is dropping, Fe2O3, and when it starts to drop, that's when you'll start to get it reduced valence form. So initially Fe3O4 is what you start to get, and there is a crossover point when this is exactly matched by that, and by this amount of reacting gas, the Fe2O3 theoretically is predicted to disappear. But then where it is going, at that, when Fe2O3 has disappeared, this one has picked. But then the predictions are that if you start going this way, then at some point you will start to get solid FeO, and then also metallic iron. So you will start to get metallic, I think this is metallic iron, this green one, and then FeO is somewhere here as well. I can't see it. FeO, purple one. So these are only predictions, and these predictions are all based on the database that the software has, right? So as you rightly say, these are all, this is equilibrium condition, which means we don't know how long it takes. This tells you that under these conditions, if you can take it to equilibrium, which can be any time, we don't know how long it is, even though you can do it for discrete times and discrete temperatures and then do many of those, students do it, then you can find out a bit more pinpoint. But this is the starting point, that under what conditions of gas concentration, under at what temperatures, and under what gas flows, etc., you can get to where you want to go to. Okay? But this is only predictions. This is only based on the quality of the data that they have in their database, and you are not exactly sure. Even though if the software has come from a reputable supplier, then you can be sure that it the more confident of it. But this is based on equilibrium composition, and therefore the Gibbs free energy is 0. So delta G is 0, which means delta H minus T times delta S is 0. Okay? So that's what it is. This sets the maximum limit, that you cannot go, if you have this much, a certain composition of the gas, then this is the amount of Fe, FeO, and Fe3O4 that you are going to get. Whether your reactor design will allow you to achieve it, that's a different story. That's up to you. So that's why I make the comment that this is nothing but the theoretical basis for solids inventory and circulation rate. Why solids inventory? Because if you see that at the end I am getting this much of unconverted Fe2O3, this much of Fe3O4, then I know how much, I know that of Fe2O3 I am not able to use all the oxygen. Therefore, I need to supply more of it. So that's why it has an implication for the solids inventory. And that's why it has the implication for bringing it back again, circulating it back again. But this is only the starting point. The proof of the pudding will be actually in eating, as we say, through trials. Trials is the real life. These are the theoretical predictions. But nevertheless, these are very important tools within the armory of a researcher, that you go step by step from this amount to this amount to this amount. Then before going to the next level of experiments, carry out your predictions a bit more, and then decide, okay, now I know everything, so, or as much as I can be, then I will do my experiments. Okay? So I'll take another 3 more slides and then I will stop. So be a bit more patient with me. So we one of the reactors, the largest reactor that we have is the 10 kilowatt thermal reactor. That's the fluid bed. We never run it beyond 10 kilowatt thermal reactor, 10 kilowatt thermal, because then we can damage it. Too much heat release, and then interior would not be, the internals may not last. I haven't discussed it, but if you have any questions on it, think of it, ask me tomorrow morning, because we will be continuing on this theme for sure, at least tomorrow morning, because I have the chemicals part to be discussed as well. So ask it, otherwise I will not go into it. So what then he did, this another student actually did. He did run it there at different temperatures deliberately, at 700 bed temperature, 800, 900, and 1000, trying to see how much carbon conversion, no carbon stripper business, no steam injection, nothing, just the normal fuel reactor conditions, how much carbon conversion you can achieve as a function of operating temperature inside the fuel reactor. whatever cannot be achieved, that will be converted in the carbon stripper. So it's a valuable information. Now in this experiment, no steam. What is alternating CLC? Correct. So once you run it as a fuel reactor, next cycle you run it as an air reactor, the same one. Rather than having 2 reactors, I don't have that much money, and I don't have that much space, and I don't have that many people to run it. Because it's all run by one student and another helper. And after 5:30, we'll have to have occupational health and safety rules. Someone has to be there all the time. That's the rule. Anyway, so that's the meaning of alternating. But still it is CL, chemical looping. Once you have seen that you have reached a stable condition, you have reached your carbon dioxide yield steady, then you know that you have come to the end of your fuel reactor cycle. Then you shut down the cold feed, you start putting in air until such time you see the oxygen breakthrough. Then you know that it has been fully oxidized. While it is still hot, then you start the cold cycle again, fuel cycle again, reactor cycle again. Then you continue to do it. Okay. So one student did up to 35 hours, and then the next student who is doing it now, just completely, has done it 100 hours, or slightly more than 100 hours now. The data looks good. So here, what has been found is that obviously 700 is a very low temperature. Everyone knows that's expected. Then 800 is another one, slightly over. 900 is a lot higher, but surprisingly at 1000 degree it is not higher, it is actually lower, slightly lower. So we decided that perhaps we have reached the plateau, or the optimum level of temperature as far as carbon conversion is concerned. We don't need to go beyond 900 degrees. Because our coals, as I said, is very friable. So when the coal goes inside a higher temperature reactor, it's coal continuously fed. So the fresh coal, dried coal coming and immediately seeing 1000 degrees, it fragments. Then what I said is one of the problems for fluidized bed gasifier. This is, in a sense, it's a fuel reactor is a fluidized bed gasifier. That for our coals, fluidized bed gasifier is not a good idea. You'll get about 85% carbon conversion. I showed some of the data, right? Why we are losing the carbon conversion, not getting higher carbon conversion? Because fine particles were elutriating out. And the fines were generated. And fines were generated through attrition. Now you remember, now you have not just the particles themselves, the coal particles themselves, but also the iron oxide particles. Iron oxide is very hard. Coal particles, poor coal particles, when they face the iron oxides, they attract even more. So the higher temperature, it goes even more. And the student then proved that this is exactly what is happening, because we are collecting more fines in the cyclone catcher. Below the cyclone, the catch pot that we have, 2 cyclones in series, we are catching more fines there. So that's why. So you don't need to go to higher temperature. You know where is your limit. The remaining, you convert it in your carbon stripper. Okay. So how is carbon conversion measured in this case? You tell me. What did we say? 2 ways of doing it, remember? Huh? That's one way, from the solids balance, from the carbon balance in the solids. Other one is gas balance. You should never do it from only one side. because you don't know which one is which method will give you the best. So you can we can have sampling facilities. At the end of every cycle, we can take samples out when it is hot. So we had the extraction, and you need only tiny amount. So the system won't even. Yeah. So in between, just from the freeboard, you have sampling system. Open it very, very carefully. Take the sample, shut it down, switch it off. Well, so if you design your reactor well, then you can do it. The other way is to do it all at the end, which will be, you don't know the cycle-to-cycle variation of it. No. Well, not really. You are still supplying the oxygen from the oxygen carrier, which will taking it, which is which is combusting the carbon. But as I said, even if it's a very well designed reactor, you will not be able to convert. Even in a CFBC, you will not be able to get 100% carbon burnout. There will be some amount left. And this is more like a around the carbon particle, it's giving a gasification background because it's the reducing gases present in the form of the volatiles surrounding the oxygen carrier. So you will not get 100% carbon converted unless you run it at your fuel cycle, you run it under batch condition for a very, very long time. No, we are not, we are deliberately not giving a reducing environment. It's just the local reducing environment that it itself creates. So, no, I think just remember our gasification and CFB discussions. When you have the coal particle is being pyrolyzed, it's giving up its volatiles. Near the coal particles, you have the reducing condition. And you are, with respect to the oxygen carrier, it's not a reducing condition. The oxygen carrier is perhaps seeing a bit more of the oxygen coming from itself as the volatiles go in and then they combust, etc. But as far as the coal particle is concerned, the coal particle is giving up its volatile from its surface and progressively from more and more from its interior. So the coal particle is seeing a reduced form, so that will limit its carbon conversion. And that will be lesser of a problem as you go higher in the temperature, but obviously if you go too high, then the minerals will start coming out and then coat the carbon particle or the char particle and then limit the carbon conversion also. So as far as the reducing condition is concerned, it is surrounding the char particle, which corresponds to which has carbon which you want to convert 100%. But if you cannot, and why you cannot? Because of the reducing environment around it. Therefore, you just don't worry, we'll have to deal with this carbon, and where will we deal with it? Either by putting in steam or carbon dioxide, or we'll take it to a carbon stripper and burn it. Either way. So this sets the limit to how much carbon you have to deal with steam or carbon dioxide or both, or in a carbon stripper with whatever. Yeah, it's a small fluid bed. That's what people are discussing. Ideally, yes. Practically not. So this is something that you generate your experience. You really rely on your experience. But if you make the assumption that my fluidized bed is well fluidized because you have designed it that way, because you have operated it that way, then you can assume that you have taken a sample from a bed which is a well stirred bed. No. So if your fluidized bed is not becomes a fixed bed, that's an issue. But if it is a fluidized bed, or even if it is an entrained flow bed, then you can, a carefully positioned sampling port can give you quite reasonably representative sample. And this is, at the end of the day, this is only 6 inches. That's it. 150. The bed. Freeboard is 8 inches. So it's quite representative. If it was a large fluidized bed, say 3-4 meter diameter, that's a different thing. That's where you may have to have different sampling locations around the same level. Any other question? Initially not, but then you, because you have the data from your small scale experiments, when you run the larger scale unit, you see if there are any differences. If there are no differences, you know you are operating it in the same way it has been designed in this. The design follows the right scaling up procedure. If not, then you take other actions. Either for scaling up can go completely wrong, or other actions means go back to the drawing board as far as the design is concerned, which is very unlikely, or operate it so that you get a well fluidized condition. Yeah. Same metal oxide was used, yes. So we are correct. So we are not removing it. Otherwise, you will lose the information about its own history. About 5 minutes and 3 minutes. So within the case. You can take from there too. So you do it different ways. You take it from every cycle, or every 5 cycles you take samples, as we are doing now, because we have so much knowledge about this rig. Several students working, but also you can take the samples right at the end when you have completed an experimental campaign, a test campaign. You take, everything has cooled down, you unload all of the materials from the bed, you unload all of the materials from the cyclones, you mix them, you take several samples from the well mixed samples ex situ, subject them to analysis, and then see overall whatever carbon conversion you are calculating, does it match with the carbon conversion calculations, carbon conversion measurements from the individual cycle-based or 5-cycle-based samples or not. So easy to do. Only thing is needed is just careful sampling and the patience. No shortcuts. But technically very easy. Simple. Any other question? So one more slide and then go to the lab. So this is the observation that we came to, that for any future tests, we will not go above 900 degrees centigrade for this particular coal. So that's it. And then we will go to the longer term tests, which I think I'll be better have to start tomorrow. Yeah, because this is showing me that going to 1000 degrees unnecessarily we are wasting our time. Because we have reached the limit for this rig. No. More fines were generated under the condition in the reactor. At 1000 degrees, there is more attrition, which generates fines. So there is no point going beyond 900 degrees. And where do the fines found? From the cyclones. Cyclone catchpot, sorry. Cyclone catchpot. Okay. So fluidized bed. Our coals, no packed bed, because our coals, we cannot get this chunk of coal. I mean, it will simply drop. It will simply break down. So in our coals, even if you are feeding this chunk of coal, this large diameter coal, it doesn't have many meaning because it loses its identity immediately during the feeding. So I think we'll stop at this point. It's almost 5:45 today.